des questions, en tout cas, n'hésitez pas à m'interrompre pendant que je parle.
Okay. Okay.
Il n'y a aucun problème.
So Benjamin, I am very happy that you agreed to give a talk to this seminar, to this online seminar. That's a real pleasure to meet you finally after such time. And I hope that there will be some some real meetings soon. I don't know how it will be possible anyway. So I let you speak and give your talk about sparsity and modeling of it's not especially for time series, it is sparsity in general.
Yes, that's true. Yeah, yeah.
Okay, so thank you, and I let you speak. Okay.
Okay, thank you very much, Paul. Hi, everyone. Thank you for joining this seminar. It's a real pleasure to discuss about sparsity. So this talk will be dedicated to the sparse modeling. The main properties we usually look at when we are interested in sparsity. And I'll try to illustrate the relevance of sparsity and sparse modeling through two applications. One in time series models and another one in factor modeling. So I'm Benjamin, by the way, from Osaka University and Riken. So I'm based in Japan. So first of all, I'll try to set the ideas of what I mean when I discuss about high-dimensional statistics. I'll go through the sparse modeling and the related properties. And as I've mentioned, now we will look at a few applications. So first of all, let me set the ideas of high-dimensional statistics with big data. So I suppose that you have heard about big data. So basically, nowadays we have access to new types of data. So here I've listed now a few examples. For example, in insurance companies, they are interested when they fix the insurance premiums. They're interested in the car driver's behavior. And they use some data which come from the continuous geolocation of car drivers through the GPS system. Also, we can think of facial recognition. In finance, also the price sequences of financial assets. And when people are interested in technical analysis, they use a broad range of indicators and the like. Okay, so the common feature of these data is that they are massive. Okay, and large data sets may allow for more flexible relationships than the simple linear regression model. So that new statistical methods are required to analyze the relationships among these data sets and perform prediction. So high dimensionality in this talk is about the large number of parameters that we would like to estimate. So in a parametric and semi-parametric setting. It concerns variable selection and common feature extraction. So to illustrate a high dimensional problem, here I've chosen this multivariate linear time series model. So the VAR, vector autoregressive model. So there we have YT, a vector, n-dimensional random vector, and we have a sample. The sample size is capital T. So we have this simple var1 process. UT is a Gaussian. Is a Gaussian error centered with variance covariance sigma. So the parameter vector here is denoted as beta, and the total number of parameters in this model is, so the complexity is n squared. Okay, so n squared coming from phi, and the parameters of the variance covariance matrix sigma, nn plus 1 over 2 parameters. Now the point is that when you have more variables, so when n is larger than t, the sample size, then we've got an issue because there are more parameters to estimate than observations. So we have what's called a significant model complexity. So this raises issues regarding the estimation of phi and sigma. So let's consider least squares based estimation. So here I simply rewrite the previous VAR model, using this stacked regression model. Okay, so with these vectors and matrices. So if you use the OLS estimation method, you end up with this solution, very standard. However, there's a problem here when n is larger than t. The problem is that this matrix, so the so-called design matrix, xx prime, is non-inversible. Okay, so there is a singularity issue because the rank condition is not satisfied. So basically the columns are linearly dependent. So in econometrics, the vocabulary multicollinearity is commonly used to express this identifiability issue. Or in statistics also, we use the so-called overfitting issue. Okay, so more variables, n larger than t, implies that this matrix is singular. Now, how can we fix this problem? So here I have listed 3 solutions. The first solution I thought about is the factor modeling. So the idea is consists in specifying some factors in the VAR dynamic. So this idea originates from Stock and Watson. So now YT is specified with this linear dynamic. So phi, the phi matrix, now is replaced with this matrix product, BA, and AYT minus 1 becomes what's called a vector of factors, F. Now the point is that this vector, the size of this vector is much smaller than YT. The B matrix, so the size is n times q, so the size of the vector F is q. Q is much smaller than n, contains, for example, the beta coefficients from the so-called asset pricing theory. Okay, so these factors are observable here. So the vector of interest now becomes B, and still the elements of the variance covariance matrix sigma. So that in total, we end up with this number of unknown coefficients. So this type of modeling was applied to the portfolio allocation problem. So for example, finding co-authors used such decomposition in a Markowitz optimization problem, and they highlighted the gain, the statistical gain in specifying such factor modeling. However, the issue here is that somehow we need to have some priors on which factor is relevant to model my dynamic. Somehow an expertise is required to identify these relevant factors. So that's the first solution to tackle the dimensionality problem. The second solution is the so-called parameter shrinkage solution. So in there, to mention this solution, I have rewritten my regression equation with these vectors and matrices. So it's simply another way to write my stacked regression model. So now theta stacks my columns of the phi matrix. It's simply another way to write the regression model, because it's easier actually to consider such model for the purpose of parameter shrinkage. So parameter shrinkage, what is it? So actually it has a Bayesian viewpoint, and I will explain that Parameter shrinkage consists in constraining the set of parameter values. So I guess also you heard about the ridge method, so which was developed over 50 years ago now. So corresponds to the following optimization problem. So in here I have my standard OLS problem, and you see here there is an additional term, which is a norm with respect to my parameter, theta. It also depends on a certain parameter, lambda, which is called the tuning parameter. I will give more insights later on this lambda parameter. So if lambda is equal to 0, you end up with the standard regression problem. But as I've mentioned, we have a dimensionality issue. So when lambda is non-zero, you end up with such solution. So now my design matrix, x prime, x tilde prime, x tilde, comes with this lambda times identity matrix component, such that depending on the calibration of lambda, you will obtain a positive definite matrix. So it has, for people who are interested in a Bayesian viewpoint, it has a Bayesian interpretation, actually, such this solution. So my ridge estimator corresponds to this maximum a posteriori. So this density here, this P density, corresponds to this product, Pyx given theta times P theta. So P theta is the prior distribution on my parameter theta, and this guy here is the likelihood. So when you specify a Gaussian, a normal prior on theta with this variance, covariance, and when P yx given theta is a Gaussian likelihood, then you obtain this solution in here. Okay, so it has the ridge problem corresponds to specifying a Gaussian prior on theta. Now, what happens if you change this prior? Let's take now a Laplace prior. If you take a Laplace prior, you end up with the lasso estimator. So the lasso estimator corresponds to this regression problem. So as you can see, this part doesn't change. This is still my OLS loss function. But now my additional term in here is modified. As you can see, now we take the absolute value. First remark, the absolute value is non-differentiable at 0. This will imply a very specific property on my solution. For the Bayesian interpretation, as I've mentioned, if we take a Laplace prior, so the location parameter being 0, my scaling parameter being b, so b being equal to lambda minus 1, so the larger lambda is, the more concentrated around 0 you will be. So this is my scale parameter. So if you take a Gaussian likelihood, then the posterior distribution corresponds to the lasso problem. So the Laplacian prior assigns more weight to regions near 0 than the normal prior. So as I've mentioned, the ridge solution and the lasso solution behave very differently. So let me give more insights with respect to that matter. So here you've got the ridge and the lasso estimation problems. So here are the problems that I've mentioned that I've mentioned before, yes. So here the OLS problem and this additional term for the ridge and here for the lasso. So actually this problem here can be seen as a Lagrangian problem which is equivalent to this problem under this constraint region. The same goes for the lasso. So actually there is a mapping between lambda and t. They're related. We can show that there is a one-to-one mapping between lambda and t. But the solution behaves very differently because my constrained regions are very different. So here, on the right-hand side, you have the ridge problem. And on the left-hand side, you have the lasso problem. So here is a two-dimensional problem. The residual sum of squares has elliptical contour. And as you can see, the constraint regions are very different. For the ridge problem, my constraint region is a disk in here. And for the lasso problem, my constraint region is a diamond, which implies a very different behavior because the diamond has corners coming from the fact that my absolute value is non-differentiable at the origin. So that the key difference is the following one. The ridge problem will constrain your parameter toward 0, but it doesn't set your parameter to 0 exactly, which is not the case for the lasso because you have corners. So if the solution hit this corner, then you will have 0 parameter and 0 exactly parameter. So the lasso performs what's called variable selection. Why? Because it sets the corresponding parameter to 0 exactly. So that's the key difference. So this is a two-dimensional problem. So in higher dimension, we have a rhomboid. So we have much more corners, which means we have much more opportunities to set to 0 the coefficients. Okay, so that's the key difference. Having a non-differentiable constraint region, so non-differentiable at the origin, will imply that you foster sparsity. Sparsity means that you foster 0 parameters. I will discuss more sparsity and the motivation to specify sparsity. Okay, and I hope also we are clear from a Bayesian perspective on the difference between a Gaussian prior and a Laplace prior. All right, and so actually also here's a problem that I would like to raise, which is the existence of a trade-off between changing the parameter and taking into account the parameter weight. So what I mean here, this raises the issue of the sparsity structure in the parameters. So for example, if we go back to the VAR model and you apply it to stocks, so the Nikkei index. So inside the Nikkei, you have large companies and smaller caps, company sectors, and the like. So that you want to specify, you want to constrain your parameters differently, depending on the size of the companies or the company sectors and the like, such that there exist different types of penalty functions which foster sparsity, taking such problem into account. So here's the group lasso. So as you can see here, the group lasso is specified with this, still my OLS problem, but with this term in here. So this part, I haven't really been clear on this, but this part is called the penalty function. Okay, the penalty function for the lasso is this one. So this guy here is called the penalty. So here my penalty corresponds to what's called the group lasso. So this penalty is non-differentiable at the origin, and it will foster sparsity at a group level. So a group of parameters will be set to 0 exactly. Okay, so here the point that I really want to highlight is that we can use different types of penalty functions to foster, to specify a very different sparse structure in the solution. Okay. Once again, the important point is to consider non-differentiable penalty functions to foster sparsity. So the sparsity assumption can be motivated as follows. So data with a large number of variables relative to the sample size are increasingly common, as I've mentioned before, with the big data environment. And high-dimensional data actually arise through a combination of two phenomena. So the first phenomenon is that data may be inherently high-dimensional, in that many different characteristics per observation are available. And even when the number of variables is relatively small, actually researchers rarely know the exact functional form with which this small number of variables should enter the model of interest, such that we are faced with a potentially really big set of covariates which enter the model, but we don't really know how to use them, actually. So the key concept underlying the analysis of high-dimensional data is the concept of dimension reduction or regularization. So actually sparsity, regularization, and dimension reduction are quite equivalent words. So producing a useful forecasting model requires regularization. So that means that the estimates must be constrained so that the overfitting issue is avoided. And so that useful out-of-sample forecast can be obtained. So now let's put a little bit modeling in sparsity. So now let's say that the parameter of interest is theta. The sparsity assumption can be formulated as follows. So we define this A set. So this is called the true underlying support. So this set is a set of indices for which my true parameter is non-zero. And we denote K0 the cardinality of A. And the sparsity assumption means that K0 is strictly smaller is much smaller actually than D. Okay, so that's the sparse assumption. Now, A is not observable. What we do is that we apply a penalization method or a regularization method to obtain an estimator for A. For example, we can use the lasso. We can use the group lasso. If we do that, we're going to obtain a sparse solution because we will set some parameters to 0 exactly. Now, the penalty or the regularizer, so both are equivalent. The penalty or the regularizer refer to the same thing. What is it? So this is a norm with respect to the parameter, which is non-differentiable at the origin. Once again, the lasso, this is the L1 penalty. The group lasso is the L1, L2 penalty. And the penalty depends on a tuning or a regularization parameter that enforces a particular type of sparse structure in the solution. So the tuning or the regularization parameter is the lambda parameter. So this guy here. So this guy here is very important actually in my solution and also from a theoretical viewpoint, because the way we will calibrate this lambda will imply a very specific behavior in my estimator. Okay, so that's the key point, I think, to remember when we think of penalization. Now, let's give more precise framework for sparsity, sparse modeling, and more precisely, sparse M estimation. Sparse M estimation or penalized M estimation. So let's have a look at this criterion. So what we have is that we have an N sample. So here it's for IID setting, but it can be also for time series framework. It's quite a general framework here. So we have a sample of observations, X belonging to RQ. So here it's for the sake of simplification that I assume such setting. We have a loss function, ln, which depends on a parameter, theta, and it can be written that way. So an average of a summation of an L function. Typically, L is a least square error, or minus a log likelihood function. And it actually can be much more general than this. However, when we will be interested in the theoretical properties of the estimator, the behavior of L, so the smoothness of L, basically, will be very important to deduce the some properties over the penalized estimator. So the penalized estimator, theta hat, is given by this problem. So this is a minimization problem. ln, my loss function, non-penalized loss function, and here is my penalty, p. So p, you remember, it's a norm with respect to my parameter, theta, depending on a tuning parameter, lambda n. Okay, lambda n is the tuning regularization parameter. So when we think of sparse modeling and M estimation, when we have a model of interest in mind, we should think of the motivation for sparsity and how to define sparsity also in the model. So I will try to answer these questions when we will look at the two applications that I propose to consider. Now for the penalty function. You remember a penalty function, I mentioned that this is a norm with respect to my parameter, non-differentiable at the origin. And actually, a huge literature was developed on specifying a suitable, with nice properties, a suitable penalty function. So you remember the Ridge penalty function was proposed over 50 years ago, but the Ridge does not foster sparsity, which is not the case for the lasso, okay, which was developed by Tibshirani. And after Tibshirani's work, a broad range of penalty functions were specified. For example, the bridge penalty function, the SCAD, in MCP. So here are the main ones that I've listed, but you can find, I'm sure you can find much more. You can find much more types of penalty functions. So the lasso is given by this one. Rho is my parameter. Lambda is the tuning parameter. The bridge looks like the lasso. However, you have this power, gamma. So when gamma is strictly equal to 1, you have a non-convex penalty, non-convex with respect to the parameter. And I will go again with respect to this non-convexity of the penalty function. So you have the bridge, the MCP, and the SCAD penalty function. So if we look at simply the SCAD here, for this threshold, actually my SCAD behaves like a lasso. Very similar, it's the same thing. So they apply the same rate of penalization. However, once we are in this set for my parameter, now the regularization rate is relaxed with this quadratic behavior. And then it becomes constant when you reach this threshold. So let's simply have a look at this graph to picture the differences between the lasso, which is convex, and the non-convex penalties, SCAD and MCP. So here you have the lasso in red, the SCAD and MCP. So basically SCAD and MCP behave very, very similar. SCAD and MCP are non-convex. So this is one-dimensional, you have one parameter only. So the point here to keep in mind is that the lasso applies the same regularization rate over my parameter, such that it will penalize large coefficients or small coefficients with the same rate, which is not the case for the SCAD and MCP. Okay, when we look at my SCAD again, it relaxes the regularization rate once you reach a certain threshold. Okay, so these are the main penalty functions. Of course, a broad range of other penalty functions were specified, such as the group lasso, so where you will force a sparsity at the group level, the fused lasso and the group fused lasso, and the like. All right, so now let's think of the properties related to sparse modeling. So here, for the sake of clarification, the properties can basically be broken down into two main categories. So first is the asymptotic viewpoint. So in that case, we are interested in the asymptotic properties of my penalized estimator. So we are interested in the asymptotic properties of this guy here, theta hat. So in that case, there are two settings. The first setting is when n only goes to infinity, and when both n and d, so the dimension also, go to infinity. So the parameter, the number of parameters is diverging. So usually d, the complexity of d, is defined as this rate, n power c. So in this, when we're interested in such properties, when we're interested in the large sample properties, the key result is the so-called oracle property, okay, which was defined by Fanelli. So it can be specified, this property, as follows. The sparsity-based estimator recovers A, and it behaves like a standard maximum estimator, M estimator. You remember before I mentioned the convexity of the penalty function or the non-convexity of the penalty function. So the lasso, the group lasso, is a convex penalty function. And this is a problem, actually, convexity of the penalty function, because it does not satisfy the oracle property. This comes from the fact that there is an inherent bias when we shrink the parameters. As I mentioned, the lasso applies the same penalization rate for all coefficients. So this is a problem, actually. And this problem is such that my lasso estimator does not recover the true subset A, except under a very specific condition, which is called the irrepresentable condition or the incoherence condition, but which is very difficult actually to check empirically speaking. So to fix this issue, actually, there's a method if one still wants to use lasso type penalization. So this is the adaptive version of the lasso, which was proposed by Zhu. So in that case, what we do, so this is a two-step method. In the first step, we apply a non-penalized estimation. So we have a first step estimator, which is non-penalized, and we plug this estimator in the second step objective function, which is a lasso penalized objective function, but we penalize the coefficients differently using some weights, some random weights coming from the first step estimation actually. But I don't really enter more into detail in this. Simply, if we use the adaptive version, actually we can prove that my adaptive lasso satisfies the oracle property. So here I've listed down the main works done for the asymptotic analysis of lasso type estimation. So Naitefu provided the asymptotic properties for the lasso bridge within an OLS setting, finally extended it to general penalized Lacliud framework, and they considered the SCAD, actually non-convex penalization. Okay, so here in Fan and Peng, actually, they extended it to a double asymptotic setting. All right, so this is for the asymptotic viewpoint. Another important literature is dedicated to, so what I've written here, the oracle inequalities and support recovery. So here, the point is to obtain, given a certain performance metric, is to obtain some bounds which hold with a certain probability. So actually, which hold with high probability. So, and actually such bounds will depend on the true support. So to derive such bounds, the behavior of my loss function, so the non-penalized loss function, is actually a key ingredient. So the smoothness of the loss function or the curvature of the loss function. So in the literature, for the OLS, penalized OLS problem, such type of condition, restricted eigenvalue condition, is commonly used to derive such type of error bounds. So for example, in the work of Van de Geer and Pullman, or Bickel, Ritov, and Sibakov, they used such type of condition. And actually, such type of condition can be generalized to any type of loss function, even nonlinear loss function. So with this, it can be extended using this notion of restricted strong convexity. So basically, strong convexity means that the Hessian, so the Hessian, the second order derivative of my loss function, is positive definite in neighborhood of my true parameter. And actually, restricted strong convexity relaxes this positive definiteness of my Hessian, okay, because by adding a certain tolerance term over my eigenvalue of my Hessian matrix. So this is a notion which was developed by Negaban, Ravi Kumar, and co-authors. And Low and Wainwright, or I with Fermagnon, Jean-David Fermagnon, we used such type of RSC, restricted strong convexity condition, to derive some bounds over my penalized estimator. And support recovery, which is quite a little bit different from the oracle property developed by Fan and Lee. So the support recovery means that with high probability, we can identify the true support. So Low and Wainwright, so this is a nice paper, they established support recovery for non-convex penalty functions when the loss function satisfies the RSC condition. Okay, so this is these papers in here, using the restricted eigenvalue condition. They established support recovery for the lasso, for convex problems. So in here, Low and Wainwright extended it to non-convex penalization. Okay, so I hope we are clear also on the two types of results which can be established when we consider penalized M estimation. Okay, so let's illustrate now the sparse modeling. for two models, one in time series and another one in factor modeling. So the time series application is for the multivariate Garch modeling. So actually, this is a joint work that I did with Fermenard, Jean-David Fermenard. So here, we're interested in the variance covariance matrix, okay, time series model. So let's start with this remark. In finance, there is a need for flexible and realistic joint dynamics for asset returns. But portfolio sizes may be quite large, especially in asset management, risk management. So here the quantity of interest is, as I mentioned, the second order conditional moment. And in discrete time, the usual approaches are the M-Garch or the multivariate stochastic volatility modeling. So here I just focus on this first type of family, M-Garch. The typical problems arising here in M-Garch are the following four issues. First of all, the parameterization, so the number of parameters which are involved in M-Garch modeling, up to n power 4 or n power 2. So for some portfolio sizes, this means that the number of parameters to estimate is really huge. So this is what we call actually the curse of dimensionality. So that restricted scalar cases are considered in order to reduce the dimension. I will mention this restricted specification a little bit later. So this is a way to deal with this complexity. The second problem for M-Garch dynamics is that the specified dynamics must satisfy specific constraints in order to generate positive definite matrices, okay, because we need to specify a dynamic on the variance covariance process, such that some tricks, some normalizations are usually made to generate a positive definite matrix. Also, the inference techniques exist, but there are no well-founded theoretical results actually on these estimation techniques. Usually it's made by QML, okay, quasi-maximum likelihood method. And actually, when we look at real data, these M-Garch modelings provide modest improvements in terms of forecasting performances. So now let's have a look at the modeling. We have a stochastic process, XT, which is an n-dimensional one. And we usually, it is split into two parts, XT, the mu t, so the conditional expectation, and my error, epsilon t. So mu t here for simplification. Okay, of course, we can specify all the types of models. It's not really the point here. I've simply taken it as this var1 process. Okay. The quantity of interest here is epsilon t, because epsilon t corresponds to this matrix vector product. HT is the variance covariance matrix, which depend on a parametric model. Okay, we specify a dynamic on HT. So this is the reason why it depends on theta, depends on some parameters. And eta t is a strong white noise. So HT is the variance covariance matrix, and in M-Garch modeling, it is a function of the past. So FT is the natural filtration, so my past observations. It's quite important. The multivariate stochastic volatility modeling is a little bit different. This property is not satisfied. So now what can we expect from HT? So here are 4 main points that I've listed. First, the stability by aggregation, so which is a property which can be useful in finance, portfolio allocation. Here, this point refers to the trade-off between parsimony and a sufficiently parameterized model to capture complex dynamics. We also need easy conditions for positive definiteness to generate a positive definite matrix HT. And when we are interested in estimating the dynamic, we would like to avoid an excessive inversion of the conditional variance. So especially if we think of the Gaussian QMLE, we need to invert the matrix. And in high dimension, sometimes inverting such matrix can be quite tricky. Now, for the dynamics of HT themselves, a lot of model specifications were proposed in the literature. The vector Garch, the BEKK, DCC, and the like. So really a huge literature is dedicated to the modeling of HT. And as I mentioned before, there is the so-called curse of dimensionality issue, because these models suffer from this curse of dimensionality, the model complexity. The model complexity refers to the number of parameters to estimate. So here I've taken a BEKK model. So this is dynamic on HT. So as you can see, HT depends on the past. So here are my past returns. So the cross product, and you have an autoregressive component. And omega, A, and B, they are deterministic matrices. Okay, so they are the driving parameters of my dynamic. The point consists in estimating these parameters. So A and B are not necessarily symmetric actually in this specification. Okay, so the solutions to tackle the curse of dimensionality can be broken down into 3 categories. The first solution to handle the curse of dimensionality consists in specifying scalar dynamics. So basically, if we go back to this BEKK dynamic, what we do is that we replace A and B by scalars, scalar parameter. So it's a way to reduce the dimension. And usually it's what people do, actually. This can be done also in other types of dynamics, for example, the DCC, so which specifies the dynamic on the correlation matrix. Anyway, it's not really the of interest here. Again, it consists in constraining the matrix parameters as scalar parameters. But this is questionable, no? Because if you have only one parameter to capture complex relationships, it's quite questionable. Now, another solution consists, we end up again with the factor modeling, specifying factor Garch models. It's also a way to reduce the dimension. However, once again, we need to have some a priori on which factors are relevant for the Garch dynamic. And the third solution is the parameter shrinkage method. In that case, we have the loss function. So usually in the M-Garch modeling, what we do is that we specify a distribution on eta t, typically Gaussian distribution. We apply the QMLE method. So we have then a loss function, which is this one, f, Gaussian loss function. And what we can do, we can specify a penalty function to foster sparsity. Okay. However, well, there are 2 problems in that case. The Gaussian loss function is highly non-linear with respect to the parameter. This is a very significant problem if you want to optimize the loss function using some efficient algorithms. and closed form algorithms. So this is a key issue actually. And also the smoothness of my loss function. Okay, usually when we want to prove some bounds, some error bounds on my penalized estimator, as I've mentioned before, we need this loss function to satisfy some curvature conditions. And this is not automatically satisfied, actually, if we use a Gaussian QML. Okay, so this is not really a good idea, actually, to specify a penalization using such type of loss function. Hence the idea that we came up with, which is the following one. So what we did here, I consider the vector Garch model. So what we did is that we ignored the autoregressive term, such that we end up with this dynamic. So if you have an autoregressive term, here you have plus a term which depends on ht minus 1. Okay, but we forgot it. So we end up with this dynamic. So this corresponds actually to an arch type dynamic. And it can be written as a linear model, given in here. So zeta t now is an error term, a new error term, which has conditional expectation being 0. So equation by equation, this system of equation can be seen as this dynamic. Okay, so my parameters of interest are in B and A. So these coefficients, A and B. And what we did is that, so the first important point is that this dynamic can be estimated using an OLS, a least squares type loss function, which is nice actually. And because we have closed form solutions and convexity, so it's quite nice actually. And what we did to avoid the overfitting issue that I've mentioned before, we specified sparsity on these B coefficients with the idea that from a certain lag, all my coefficients will be equal to 0. Okay, so the idea is that the most recent observation has more influence compared to the past far away observations. That's the idea. So as I mentioned, the multivariate arch process can be estimated using the OLS estimation method. And actually, when we assume that the above model is the true one, with the true index Q0, then a penalization procedure with Q larger than Q0 would likely set the parameters, the B, to 0 when K is strictly larger than Q0. If the true model is a Garch type dynamic, so it can be rewritten with Q is equal to infinity under suitable conditions on the parameters, so that it may produce relevant approximations of usual Garch processes when we take Q sufficiently large. So we proposed several conditional variance specifications which ensure the positiveness of HT, but still using a linear type of model with the idea that we will use an OLS type loss function. So we specify some Cholesky-Garch processes. And there is a numerical advantage also of the method, which is the ability to parallelize the estimation, to perform an equation by equation estimation. So for the properties, so here we established the large sample properties. So just to set the ideas of the penalized M estimation that we considered in that case. So my M estimation is given by this problem. So G is my loss function, which is an OLS type loss function, and P is a penalty function. So actually P is equal to this so-called sparse group lasso. Because we want to specify a particular type of sparse structure in my solution. So basically, it's a mix between the lasso problem and the group lasso problem. And adaptive version, because, as I've mentioned before, if you don't consider adaptive version, you cannot satisfy the support recovery property. Okay, so the sparsity here is motivated by the fact that we want to foster sparsity at a group level. So we will set to 0 groups of variables corresponding to a certain lag. And within each group, also we want to specify sparsity. So we can also establish such type of probability bound, asymptotic probability bound. And we also establish the oracle property. So we identify the true support, and we have an asymptotic, asymptotically normally distributed estimator. All right, so maybe let me go over, for the remaining 5 to 10 minutes, over the second application that I propose to motivate the use of sparse modeling, which is the factor modeling. So this is joint work with Terada, Yoshikazu Terada. So the modeling is the following one. We have a vector of observation xi, which is decomposed as a product of lambda fi and an error, epsilon I. So lambda is the loading matrix, so it contains the loading factors, and f is the vector of factors, factor variables. So f and epsilon actually are not observable, only xi is observable. So we make some assumptions on f and epsilon such that we end up with this parameter of interest. So the interest is to estimate lambda and psi in order to get a factor model-based variance-covariance matrix, sigma. Okay, so there exist a lot of types of inference methods for factor modeling. I don't really enter into detail here. I just would like to justify the use of sparse modeling in this work. So actually a broad range of studies were dedicated to the sparse estimation of sigma, sparse variance covariance matrix. A lot of works were made for that. But actually in empirical, when we're interested in some empirical applications, such sparse assumption may not be appropriate, okay? Because actually there exist several common factors for the underlying structure of the observed variables. So that factor analysis stands as the natural method to appropriately deal with the common factors. So in standard factor analysis, the epsilon I are assumed to be uncorrelated. So that means psi is diagonal, but this assumption is quite restrictive in practice, such that assuming a non-diagonal psi is more relevant and more realistic than assuming psi diagonal. But I don't really enter more into detail for this. When we assume psi non-diagonal, we have what's called approximate factor model. So what we did here is that we fostered sparsity with respect to psi. And we considered the following statistical problem. Okay, so we have a penalized loss function. So G is my loss function. And we have the penalty function, P here, which will foster sparsity on psi. So this is a two-step problem, actually, because the loss function is a function of a first step estimator, lambda tilde. Okay, because actually fostering sparsity with respect to lambda tilde in factor modeling is a very, very challenging task, actually, and I will mention that a little bit later. Okay, so basically this is a Gaussian, penalized Gaussian problem, okay, for a very suitable parameter set. I don't really enter into detail in this. We also specified another type of loss function, which is a least square based loss function. So here it's a Gaussian loss function, and here a least square type loss function. And so we derived some error bounds. So you remember, as I mentioned before, two types of properties that we can prove, the asymptotic one and the oracle type inequalities. So this is what we did here under specific conditions of my loss function, more precisely under the restricted strong convexity condition. We can derive such type of loss function. And my lambda parameter, my tuning parameter, is calibrated as here, so using this set of values. And in here, this is a bound for the least square based estimator. So actually my bounds highly depend on the curvature, on the smoothness of the loss function. All right, and I think I should end up the talk. So let me conclude with some work in progress on sparse modeling. So as I mentioned, in factor modeling, the regularization, so the penalization of lambda is a very difficult problem. Why? This is because of the identifiability issue. And because we have a lambda, so we have a quadratic product on lambda transpose. So we have what's called a rotational indeterminacy. And this is a key problem for estimating lambda and on how to specify sparsity also on lambda. So this is currently a work in progress. We can handle the regularization by considering a penalized estimation equation framework to manage this rotational indeterminacy. Another work in progress is dedicated to sparse structural VAR modeling using precision matrices. So this is based on the property that the VAR coefficients can be interpreted in terms of a directed acyclic graph, such that a sparse precision matrix of a suitable random vector provides sparse VAR coefficients. And another work is dedicated to feature selection methods, where in that case, we specify some association measure between a certain output and covariates in order to screen which covariates are relevant for my output. All right, so I finished. If you do have questions, please do not hesitate to ask if you want to have more details on some things that maybe I went over a little bit fastly. Thank you very much.
So thank you very much to you. I let you ask any questions if you have.
Yes, I have some question.
Yes.
So, thank you for the talk, Benjamin.
Yes.
Yeah, I have a question about the last bound you showed.
Here, for example.
This is with a high probability, something like this, or?
Yes. So good question. Thank you. Actually, so this one is based on a deterministic argument.
Okay.
So this is a deterministic argument, but we can prove that these bounds hold with high probability. Okay. The point is to use a concentration inequality with respect to this guy here. Mm-hmm. So between my sample variance converse matrix and my factor-based decomposition. If we do that, we can obtain that this bound hold under a certain probability.
Okay. And the second question is that, so I finish with the second question. For deriving this concentration bound, do you use did you use a mixing coefficient or something like this?
Yeah. So good question again.
Because,
so
what is difficult with the high dimension is, I suppose, is that most of the time, it is a simplification. You assume that you have a dependence coefficient that does not depend on the dimension, and it's not so easy to prove that for some models with a dimension which is approximately close to which is very close to the sample size, that the mixing coefficient can be bounded independently from the dimension.
I see.
For some setup, you can say, okay, you can define some simple setups for which you know that if you add more and more components, the mixing coefficient will be insensitive to the dimension. But if it is sensitive to the dimension, you should recover the dimension in the constant, and the convergence is not so clear. So did you notice this or?
I see. Actually, maybe the point you mentioned is a point that I still need to double check that for the Zvar model, because what we did for the Zvar model is that we derived such type of bounds for different types of loss function under certain probability using mixing properties of my var dynamic. And so thanks to this, we can derive some concentration inequality of my sample size over my variance covariance matrix. But in this problem here that I present for factor modeling, we consider IID setting, in which the variables are assumed to be uniformly sub-Gaussian.
Okay.
But in some works on factor modeling with time series, people assume strongly mixing series for the factor f and my epsilon. So epsilon and f are assumed to be strongly mixing. Usually it's the assumption which is made.
Okay. Thank you.
And may I ask also where appears the assumption that the inputs, that the noise is Gaussian?
So for this epsilon?
Yes.
This epsilon,
the other one, I think.
Sorry?
Maybe this assumption was in the other reference, but I saw somewhere the reference, the fact that some inputs should be Gaussian.
So in this specific problem here, we assume sub-Gaussian variables for f and epsilon. So this is the assumption we made. So I'm not sure if I answer your question precisely.
Okay. Also for the question of Lionel, I think that there were some specific inequalities for covariance under strong mixing, which don't involve at all the dimension. It's not a real answer to you, but in a sense, it avoids the problem of the dimension in such when you consider mixing assumption over high dimensional models.
I think I would be very interested to have a discussion about this because it's a problem I wanted to discuss, I think.
So
because
that was a result by Harold Delling, which was using an inequality from Lindenstrauss-Zafiri, which is a strong result of Banach space theory. And this inequality is quite strong and very useful to deal with high dimensional models under mixing.
I see.
Very interesting.
I see.
And okay. I have just the last question, in fact. So
yes, please.
I was wondering about the model that is called the Beck model, because you have to make a simplification at some point just to assume that it is not autoregressive. You ignoring the autoregressive term, what is written on the slide. So if you don't ignore this autoregressive term, so you have some problem because it is not convex or something like this. But do you is it possible in some sense to reduce the dimension even in this case without simplification?
The problem is if you actually why we did this, it's because this allows for least square estimation.
Yeah.
Because of this.
Of course.
If we have an autoregressive term, the only way to estimate it is with QMLE. And in that case, The dimensionality issue, the only way I think consists in constraining a priori the parameters, the B parameter. I don't really see another way actually to deal with this issue.
Because if you apply the standard penalization techniques, it doesn't converge or something like this, or you don't find numerically.
But I think yeah, I've never tried it actually, but numerically, I think it's not really efficient to do this.
Okay. Thank you.
Okay, so I suggest I just stop the record.